Professor Kashiwara has been properly introduced in front of His Majesty yesterday, so I will just restrict myself to reading the short citation for the prize. So, he received the prize for his fundamental contributions to algebraic analysis and representation theory, in particular the development of the theory of D-modules and the discovery of crystal graphs. Please, Professor Kashiwara, the floor is yours.
So, thank you for coming here to attend the Abel lectures. So, I'm going to speak about the monoidal categories, non-commutative case. So, I was a student of Mikio Sato, who initiated the theory of algebraic analysis. So that is to study analysis. Analysis here means linear partial differential equations by means of algebra, so by D-modules. And after establishing the theory of D-modules, I wanted to apply it to other fields. And the target was representation theory. And so representation theory is a field that studies mathematical objects through symmetry, such as groups, real algebras, etc. So today's talk belongs to representation theory. Yeah. So more precisely, I'm going to speak about the monoidal categories of finite dimensional modules over quiver-Hecke algebras or finite dimensional modules over quantum-affine algebras. But I think I don't have a time to touch into the finite dimensional module, the quantum-affine case. So they have some similarities. Those two categories are monoidal categories, and all objects have finite length. So it has finite Jordan-Hilbert series. And they are non-commutative in the sense that the tensor product of two objects, x tensor y, is not isomorphic y tensor x. But there is so-called universal matrix which connects M tensor n and N tensor m. However, the problem is this universal R matrix may vanish or it diverges, and so you have to give a sense to the universal R matrix. And so it is non-commutative, so it cannot be isomorphic. So, and moreover, those categories have different features from a commutative case. That is why I started to be interested with non-commutative case. And that is the subject of my talk today. And my today's talk is based on joint works with Korean mathematicians, Sok-Jin Kang, Myung-Ho Kim, Se-Jin Oh, and Woo-Yeon Park. Okay, so I'll explain monoidal categories. So as you know, there is set. Of course, set consists of elements, but set is only the element. So we need more rich structure. So now it is given by the category. So category consists of two types of objects. So objects and the relation among objects. That is given by morphisms between two objects. So that is a category. So more or less, set corresponds to category with a richer structure. And there is so-called additive category. Additive category is a category which satisfies some conditions. In particular, home space, the set of morphisms between two objects, is an abelian group. And there's a more sophisticated one, so-called abelian category. I will not explain the detail about it, but that is also an additive category with certain properties. So it corresponds more or less to abelian groups in the set theoretical point of view, and it corresponds to abelian category. And there's a more richer notion, monoidal category. Monoidal category is a category endowed with a bifunctor, that so-called tensor product, bifunctor from C times C to C, which satisfies certain properties such as associativity and so on. And there is the conjunction of abelian category and monoidal category. So that is a monoidal category, and that is abelian, and moreover, the tensor product is exact. So more or less, abelian category corresponds to the abelian group, and the abelian monoidal category corresponds to ring. Ring is an abelian group together with multiplication group. Okay, so there's the notion of Grothendieck group. So that goes from category to set. So for an abelian category, so you can consider the Grothendieck group. It consists of it is an abelian group generated by the isomorphism class of objects of C with such relations. If there is an exact, so-called exact sequence, so I will not explain about that, but L is the kernel of the arrow from M to N, and N is a co-kernel of the arrow from L to M. So in that case, M is L plus N. So that is only the defining relation. So that is a Grothendieck group. And if every object C has a finite length, then K of C, the Grothendieck group, is a free group generated with a basis consisting of simple objects. So that is a very good part, because the Grothendieck group has some canonical basis consisting of simple objects. And if she is abelian monoidal category, then the Grothendieck group is in fact a ring by the multiplication is given by the tensor product. So that is a dictionary. So which correspond to abelian monoidal category to ring, and abelian category with the abelian group, but by means of the Grothendieck group. Okay, I'll give some examples, but they are commutative case. Yeah. So the simplest case is the abelian monoidal category consisting of finite dimensional vector space, say, over the complex number field. So that is a abelian monoidal category with the usual tensor product as a tensor product. And its Grothendieck group is isomorphic to Z with a basis that is one-dimensional vector space, the complex number itself. So that is very simple structure. And another example is a little bit more complicated, but not so much. So you consider the multiplicative group So consisting of n tuples of non-zero complex numbers. So that is a group by the piecewise multiplication. So the representation of this multiplicative group is nothing but a pair of a vector space, finite dimensional vector space, with a group homomorphism from this multiplicative group to the automorphism group of V. And then that is, again, an abelian monoidal category. And the representation, the Grothendieck group is just the Laurent polynomial series, the set of Laurent polynomials of x1 to xn. And that is given by the trace of rho. So here, n tuples of elements in complex, non-zero complex number. You take just a trace, the so-called the character, then it gives a Laurent polynomial. So by this correspondence, they are isomorphic. So as I said, the simple objects of the of this monoidal abelian category consisting of simples is a basis. And it corresponds to the monomial in the polynomial, in the Laurent polynomial ring. So that is obviously the basis of the Laurent polynomial ring. So that is a rather simple examples. And here, there is a little bit more complicated example. So the representation of the general linear group. So that is a general linear group that consists of n by n invertible matrices. And that forms a group by the multiplication of matrices. And so that is a category of finite dimensional modules over the general linear group. So that's the same thing, consisting of finite dimensional vector space together with a group of homomorphism from general linear group to the automorphism. So that is, again, an abelian monoidal category. And its Grothendieck ring is, in fact, so there is a map from the if you have the representation of GLN, then the multiplicative group is embedded into GLN by the diagonal matrices. So you have the algebra homomorphism from the representation of GLN to the representation of the multiplicative group. And that is, in fact, embedding, and it corresponds in this way. So the representation of the multiplicative group is not isomorphic to the Laurent polynomial ring. And this Grothendieck group of the representation of GLN consists of the symmetric Laurent polynomials. And so similar to the other case, the simple object of the representation of GLN gives the basis of the Grothendieck group. And so that is a basis of the symmetric Laurent polynomial algebra, and that is embedded into of course, into this one. And that corresponds to the so-called Schur polynomials as the subset of Laurent polynomials. So that is a basis. So you have some good basis of symmetric Laurent polynomial consisting of Schur polynomials. So that is a good way. So I think so the ordinary Schur polynomial arises in that way. And so we say that this phenomenon, I mean, so here the algebra of symmetric Laurent polynomials, and that is isomorphic to the Grothendieck group of the representation of GLN. So in such a case, we say that the Abelian monoidal category of the representation of GLN categorifies the symmetric Laurent polynomials. And so the advantage is one part is so you can give a basis of the Laurent polynomial ring consisting of Schur polynomials. Moreover, we have the positivities. So it means if you have two Schur polynomials and you consider product, then because that is Schur polynomials forms a basis, that is a linear combination of Schur polynomials with some coefficients. But this coefficient must be positive. Why? Because if you consider the product of two representations, then if you consider the Jordan-Hölder series of extensor Y, then you can get represent it by finite many simple modules. So it is a sum of finite many simple modules. So that is a very trivial fact, but it implies the positivity. This positivity is not obvious, but you can say because of the categorification, we can prove that the positivity of Schur polynomials. So that is an advantage of finding the categorification. Okay, so those categories of complex number, complex vector space, or the representation of multiplicative group, or the general linear group, they are commutative Abelian monoidal category. Commutative means x tensor y is isomorphic to y tensor x. Now, we shall give an example of non-commutative Abelian monoidal category that have a very different feature. Some part is similar, but there are many interesting phenomena appears, particularly in non-commutative case. That I'm going to explain. So here I'll take the so-called Quiver-Hecke algebra. Sometimes it is called KLR algebra. So because this algebra is introduced by Ruquier and Kovanov-Lauder independently, so taking their initials, we sometimes say KLR algebra. So that is generated by some elements, E of nu, xk, tau L. E of nu are idempotent, xk are some commutative objects, tau L is a variant of transposition. And they satisfy some defining relations. But I think you don't need to read it because so that is too complicated. So they just, as I said, you have new idempotent, and xk's are commuting objects, and tau L is a kind of transposition. So SL is a transposition of L and L plus 1. So it is something like the transposition. And so that is a non-commutative algebra with some certain properties. So that is in fact connected with some polynomials and Qij, and I'll take some special case so that it corresponds to the so-called AL or SL, special linear group of L plus 1. So that, I think that is rather technical, so I will not go to detail. So this Kuiper-Hecke algebra is a graded algebra. So the grading is, of course, the idempotent must be degree 0, and degree of xk is 2, and so on. And we consider the category of finite dimensional graded modules of a Kuiper-Hecke algebra. And Kuiper-Hecke algebra depends on the number of variables n, and you consider the direct sum, and it is from the abelian category. So RG mode. And there's a Q, the grading shift factor. So grading shift factor is you shift the grading by 1. So there's another one. So if you take 2 integers, then R of m times R of n is a subalgebra of R of n plus n, so that we can define so-called the convolution product of 2 modules. One is R of Rm module, and the other is n modules. The convolution is given in this way, so by using this embedding. So that gives a tensor product of RG mod, and so RG mod is an abelian monoidal category with this convolution product as a tensor product. And that is in fact non-commutative. So, but it's Grothendieck group is an algebra, because that is RG mod is an abelian monoidal category, so that is an algebra. Moreover, there is a shift factor, grading shift factor, that is invertible, and so that is in fact this Grothendieck algebra is a ZQ inverse algebra, and that is in fact we can describe the Grothendieck algebra very explicitly. That is the so-called the quantum coordinate ring. So I will not explain about that, but that is the algebra generated by this one, and perhaps it's not important, but I think, so that is non-commutative, but at Q equal 1, so if you divide Q minus 1, so that is the polynomial ring over the upper triangle important matrices. So here is 1, x1, x2, and so on. So those are indeterminates, the coordinate of the upper triangular matrices, set of upper triangular matrices. And it is isomorphic to the polynomial ring over this set. So this Grothendieck ring explicitly is described explicitly the quantum ring. So it means that, I'm sorry. So as I said, RG mode categorifies the quantum unipotent ring. Yeah. So similar to the commutative case, simples of RG mode forms the basis. And in fact, it corresponds to some basis of the unipotent coordinate ring, quantum unipotent ring. And that is so-called the upper global basis. And that is some good basis, but I'm not going to explain about that. So it gives some good basis of the quantum unipotent ring. Moreover, there is a positivity. That is the same. So to the GL case, the commutative case, if you have 2 elements in the basis, in the upper global basis. Then the product is a linear combination of some bases with non-negative coefficients. So that is the positivity. So the categorification theorem gives the positivity as a very easy corollary. And it explains why the positivity holds in such a case. So I think if you have some positivity condition, then you can expect that there is some good categorification. So, but this is non-commutative. And so there is some particular phenomena for non-commutative case. So that is the first one is so-called universal enveloping algebra. It is universal R matrix. So you have some morphism from the M convolution N to N convolution M. That is a factorial in M and M. And it satisfies some good condition. So that is more or less you swap M and N. And so it means, here it means you swap L and M, then L and M. So that is equal to you swap L and M tensor N. So they are equal. And so it gives also this condition. You swap, there are three of modules. You swap L and M and N in two ways to arrive the convolution in the opposite direction. LMN goes to NML in two ways. Then they are same because of those actions. So it is a good morphisms, but unfortunately, it is not isomorphism. It's far from isomorphism. It may vanish. So then, if it vanishes, of course, there is no advantage to introduce the universal R matrix. But there is some trick to avoid it. So that is affinization. So say there is an isomorphism, so Z is an indeterminate. Then you map xi to xi plus z, then that gives an automorphism of R added by the generator Z. Then for a given module, you can twist, you can get this new module. So that is a module M tensor kz, but the action is twisted by this automorphism. Namely, for example, xi tensor f of z is an element of the polynomial in z, and u is an element of M. Then that is by z times x. The sum of the multiplication of z and the multiplication by x. In this way, you can get a new module, M, the affinization of M. Then, if you consider M and N, and you take the affinization, then you have the universal R matrix. It is isomorphism menomorphical in Z. So it means that it is an isomorphism after tensoring KZ Z universal. So the universal R matrix itself is not an isomorphism, but if you add Z and you twist the action, then you can get isomorphism between two modules. You can swap to the order of the modules. So it means there is some n such that there is the largest n such that m tensor n f goes to nf tensor m multiplied Zn. So you can divide it Zn, and then at z equals 0, it gives a non-zero morphism, R. So that is so-called normalized R matrix. So I can repeat it. So you have universal R matrix. Universal R matrix itself can vanish, but after the help of affinization, you can get a non-zero homomorphism from M tensor M to M tensor M. But it may vanish. No, I'm sorry. It is not necessarily an isomorphism. Okay. So now this is a very particular feature in the non-commutative case. That is so-called real module. So that notion is introduced by Bernard Leclerc. We say that a simple module is real if M tensor M is again simple. So it is not all the case for vector space case. For example, for vector space case, only one-dimensional representation is real in that sense. So there are, but in non-commutative case, there are many interesting real modules. So for example, in the Kuiper-Hecke algebra case, so that is parameterized, it corresponds to some AL, so that corresponds to SL, L plus 1. In the Dynkin diagram notation, that corresponds to AL. And L is a positive integers. And if L is at most 4, then any simple is real. But L is larger than 4, then there exists imaginary. Imaginary means not real. Imaginary simples. So that is what Leclerc found. So perhaps it's better to explain why Leclerc considers such real simple modules. So then I have to explain about the so-called cluster algebra. So I explained already the Grothendieck group of the Kuiper-Hecke algebra modules is isomorphic to the quantum affine algebra. And at Q equal 1, that is just a polynomial ring, so that is commutative, of course. And so AQ of n is a Q deformation of some commutative ring. And so we can expect perhaps the basis, the upper global basis, has nice multiplicative properties. So that is, I think that is the original idea of forming Zelevinsky or Berenstein when they introduced the notion of cluster algebras. So I will explain this in our context. So here there is a basis, the upper global basis. So there are first naive conjecture. It turns out it is not true, but so there is a family of finite subsets of this space, such that so if you take any member of this family, then they are commuting up to a multiple of Q. So xy is y. It is not exactly yx, but up to the power of Q, they commute. And another one is if you take a member of F and C monomial. Any C monomial belongs to the upper global basis. Here C monomial is the product of elements in C. And because they are commuting up to a multiple of Q, so this monomial is determined up to power of Q, the multiple of Q. So other condition is maximality. So if an element Q commutes with all members of C in F, then this B is again a C monomial. So it means more or less the C mono. If you fix C, the C monomial is a maximal commuting family. And finally, they say that the upper global base is the union of C monomial where C range over F. So I think that was the original conjecture. But it turns out it is not true, and Leclerc gave a counterexample. So because he found non-real imaginary vectors. So B, an element in the global basis, is real if B square is again a member of the upper global basis. So it means the corresponding simple module is real. And so any C monomial must be real if you assume those conditions, because any C monomial belongs to B. And the square of C monomial is, of course, a C monomial. So any C monomial must be real, but Leclerc found imaginary, non-real vector. So it means this condition, the last condition, the upper global basis is a union of the cluster monomials. So that is false. So that is why Leclerc introduced the notion of real vectors. Okay, so you cannot expect this condition. Any element is a C monomial for some C. So you have to replace it a weaker condition that the algebra is generated by the cluster monomial as algebra. So that is the notion of cluster algebra. Of course, they put more very nice way to find F, but I think that is I'm not going to explain. So-called the notion of mutation, that is most particular phenomenon in the cluster algebra, but I think I'll not explain about that. So those element C is called cluster, and C monomial is the element is called cluster variables. So Fomin-Zelensky introduced the notion of cluster algebra, so that is the algebra generated by cluster variables. But I think it's not one. But so what happened is this AQ of n is a cluster algebra. So you can define the many commuting family of the AQ of n, maximal commuting family of AQ of n. Okay. So, but there is another feature of non-commutative one. So he introduced Leclerc introduced real modules, but real module is important not only because of that, but in other context that I'm going to explain. So you consider home space, So there is a shifting operator, grade shift operator. So that is, if you shift n, then we say that is a homomorphism of homogeneous of degree n, and that is the sum of the morphisms of homogeneous of degree n. So I think that I'll give another notion, m delta n. So that is a circle of m tensor n. And the circle is the largest semi-simple subobject of m tensor n. Semi-simple means a direct sum of simple objects. And m nabla n is the head of m tensor n. The head is largest semi-simple quotient of m tensor n. So there I introduced this notion. And so here, that theorem is very particular to the non-commutative phenomena. It arises only non-commutative phenomena. So assume that m and n are simple modules, and one of them is real. Then we have m tensor n has a simple head and simple circle. That is, m tensor n has a unique simple submodule, and it has a unique maximal proper submodule. And moreover, the homomorphism from m tensor n to m tensor m is one-dimensional. So that is R. So, and the most important one is, so now you have the R matrix. That is a morphism from m tensor n to m tensor m. It swaps m and n. And the image is equal to the simple head of m tensor n. So image is, of course, the quotient of m tensor n. And that corresponds to the head of m tensor n. And, of course, image is a submodule of m tensor m. And by this identification, that is equal to the simple circle, the largest semi-simple object of m tensor n. So that is the theorem. And repeating this one, if you have two modules, simple modules, and if one of them is real, then the image of the non-zero module homomorphism is in fact the simple head of m tensor n and the simple circle of m tensor n. Of course, this is true. We have to assume this condition. One of them is real. Because if m is equal to n, and m is not real, then m tensor n is not simple. So, and there is an identity from m tensor n to m tensor m. So if this holds, it must be identity. So m tensor n must be simple, but it's not true, because if m is not real, m tensor m is not real, not simple. So this is, for to have this theorem, one of them must be real. And so the notion of reality is important in this sense. And another feature is, so that gives a way to produce simple modules. Usually, to get simple modules is not easy, because simplicity is module has no submodules, and it is not easy. And so that gives so by this method, you have two modules, and one of them is real, and you take the image, then you can get a new one. So in this way, you can get a simple module starting from simple modules. So that is the case, in fact. I think that the time is running. So I think I will not explain the other things, but I want to say that the real, so in this way, non-commutativity have some interesting feature. So I only explained here. Real, the notion of real module is important because of those theorems. And there are many interesting features in non-commutative monoidal categories. So I think that I'm now 78 years old, and yesterday I saw King of Norway, and he told me that that's not exactly in that way, but he is at 88 years old, and I have another 10 years to go at least. So, so I think I want to continue this work to clarify the structure of non-commutative monoidal categories. Okay, thank you very much. Yeah, I think, yeah.
Thank you very much, and we open now up for questions or comments from the audience. We will use the microphone, so please raise your hand and wait for the microphone.
Thank you for the talk. I'm curious, going back to the beginning where you discussed categorification, where you described your algebras as coming as the Grothendieck groups of monoidal categories. Is there now a kind of standard, I don't know, uniqueness results or some kind of understanding of when this art becomes a science?
But I didn't catch your question.
Are there axioms or something that controls when you have the right to call a category categorification?
Yes, there can be. Yeah, but so I think there are other. So at least I mentioned two categories. I mean the categories of the categories of modules of quiver-Hecke algebra and quiver quantum affine algebra. So there are two examples, and another example is a category of pervasives over some types of fragment manifolds, and that gives also the affine or context affine. And in fact, there are some works on that. And I think more or less the important part is, so as I said, the similarities. So there is some kind of R matrix and affinization. Then more or less all that argument works.
Thank you. Are there further questions?
I have somehow a vague question. Related to these R matrices you mentioned, you looked at poles and zeros of these R matrices. You looked at poles and zeros of these R matrices. So you had these R matrices?
Yes.
And you looked at when does it have a zero and when does it have a pole? And so is there a general result how big, for instance, these poles can become? What is the sort of biggest number you have to invert the Z to the power? Is there a description how this?
Sometimes, I can say sometimes, but there is a way. And I think that part is important feature, but personally, I have no time to explain those details.
A final question? That does not seem to be the case, so let's thank Professor Kashiwara once more.